Hello, my name is Jake Kim.
My name is He.
And my name is Jason Lenh.
Alright, in this presentation, we're going to look at how to optimally tour the continental US. Alright, we'll start with this presentation by establishing the framework and premise of the tour optimization problem. Then we'll introduce the mathematical and computational concepts behind our analysis, and we'll present the results of our analyses from applying the shell heuristic as well as simulated annealing to two of our data sets. And an analysis of possible alternative scenarios will follow, and we'll finish with the conclusion of our analysis, including our chosen tour and justification for our selection of it.
As ambitious Hopkins students, we are planning to complete an epic road trip of the continental United States, visiting all 48 contiguous states, starting and ending in Washington, D.C., and being tri-hat AMS students in particular, we want to optimize this tour, minimizing distance traveled. In each state, we will visit one city of interest that best represents the state.
Our criteria for selecting the city for a given state from most to least importance are as follows. 1. The size of the city, where we prefer metropolitan areas. 2. The popularity, in other words, how often the city is visited by tourists. 3. The historical background of the city, which includes state capitals and historical cities, which will be preferred. And 4. Personal preferences, such as visiting hometowns and/or other points of interest.
In this slide, we have a list of all the cities that we'll be visiting. Just to highlight a few areas of interest, we have San Diego, California, a quintessential coastal California city. We have Seattle, Washington, an Instagram perfect place, and Philly, one of the oldest and most important cities in the United States. There are several ways to calculate the driving distance between cities, one being Haversine distance approach, which is based off of Euclidean distance, and then the other being Google Maps data. We decided that we're going to use the most accurate data, which is the Google Maps data, to calculate the actual amount of driving distance and driving time expected when traveling. And because Google's extensive data collection for travel time yields more accurate estimates for travel time, that's another reason to use that data. This will be executed by writing a Python script that accesses the Google Map API and then parses the output. We'll have this script available in the appendix at the end of the presentation.
Before we discuss the specifics of our analysis, we would first like to lay out the core assumptions that were necessary for the analysis. They are: first, each city is visited exactly once in the route, except for the starting city, Washington, D.C. Second, the map is well connected, that is, every city can visit every other city with no restrictions. Third, distance and travel time are symmetric, so that the distance or time traveling from A to B takes the same amount of time traveling from B to A. Fourth, distance and travel time have a linear relationship. That is, there are no sections of traffic or speed limits that will affect travel time for a given section of the tour. The last one, the data obtained from the Google Maps Distance Matrix API are accurate estimates of driving distance and time. It should be noted that Google Maps incorporates some degree of average travel speed in certain stretches of road. This may serve to improve the accuracy of our results from analysis.
The first of the approaches that we will use is the shell heuristic. The shell heuristic is often used to solve the traveling salesperson problem. The initial step of the shell heuristic is to construct a convex hull, which essentially is the smallest convex set that includes all the points in the set, either in the interior or in the boundary. This is the beginning of the tour. Afterwards, each point not in the convex hull boundary, in other words, is in the interior of this convex set, will be selected, and the cheapest insertion for this point will be found, thus adding it to the tour. The output for the shell heuristic for an assembly of points is shown on the right, and was generated using MATLAB. The code for this can be found in the appendix at the end of the presentation, to be viewed at your leisure. For our first approach, we employed the shell heuristic using the Google Map data, which yielded a total driving time of 202.01 hours and a total driving distance of 13,099 miles. Notably, in the Louisiana region, it was found that there was some crossing in the tour, which generally can be understood to be an inefficiency in the route.
For simulated annealing, the algorithm defines optimal solutions by global and local searches. It begins by constructing a random tour, from which it continually attempts to improve the solution by random mutations to the current solution. In the initial global search phase, it'll have a greater tendency to move in suboptimal patterns due to the inclusion of a stochastic element that determines inclusion or rejection of a new solution that's moving towards a direction that worsens the objective function. If it improves the objective function, it will be accepted. As the search becomes more localized, suboptimal search directions will be less accepted until the search becomes strictly along the direction of improvement.
Here gives the best solution for simulated annealing. The total driving hours is 220 and the total driving distance is 14,208 miles. Comparing with the result we obtained in shell heuristic, we can find that the simulated annealing gives a worse result. This may be because simulated annealing is more stochastic, that it starts from an efficient solution, and there is no guarantee that the final solution will be a good local minimum that we would like to accept. Considering our safety, our plan is to drive no more than 10 hours at any one time. In addition, once we arrive in a selected city, we plan to spend 8 hours visiting various sites. Apart from this, because we are human, we require 8 hours of sleep for every 16 hours. Our sleep schedules are highly flexible. That is, we can sleep during the day. This is a quite reasonable assumption given our lifestyle at Hopkins. There are two potential solutions to this problem. The first is that we can modify which city to visit to reduce driving time. Or we can break longer drives into multiple paths, each no longer than 10 hours. Also, sleep in the car on the highway is acceptable. How we implement these solutions will be discussed at a later slide.
In addition to the previous constraints that we have set, we may wish to incorporate 8 hours of touring each city into our schedule. Naturally, several changes will have to be made to the departure date beyond just the driving time for this modification. However, in our assumptions, which 8 hours of the day assigned to exploring the city are not particularly important. Naturally, this is clearly not an ideal assumption to make, because certain events or festivities specific to the city are best enjoyed at a certain time of the day. For example, Las Vegas is best visited at night. Also as a goal, in accordance to events in our lives, such as academic or occupational obligations, we want to complete the tour by August 31st, and thus want to identify the appropriate departure date to achieve this goal. In correspondence to this, it may be necessary to modify the itinerary or touring schedule to accommodate for this. However, for our analysis, we simply move the departure date forward to adapt to the schedule of our needs.
As for determining the departure date in order to arrive back at the origin, Washington, D.C. by August 31st, we evaluated mostly two top methods. First being the stopping on the way without altering the itinerary itself, and the second method being artificially setting an arc cost to a large value, some large value m, to dissuade inclusion from the simulated annealing method. What we settled with eventually was the first option, to stop along the way without any changes to the itinerary, mostly for practical reasons, and also to not mess with the model too much, especially when we're doing what-if analysis and when we start changing the constraints. So, for example, using this method, we observe the output. So, for instance, for the shell heuristic using Google Maps data, we identified two segments that had to be broken up from Portland, Maine to Detroit, Michigan. That's slightly over 10 hours. Another segment from Eugene, Oregon to Las Vegas, Nevada, of about 14 hours. And we can see these being calculated for other models as well. Going over the results for determining departure dates, let's see the top three methods used here for the shell Google Maps, shell Euclidean distance, and the simulated annealing using Google Maps distance. Google Maps using the shell heuristic gave us the shortest distance in terms of both driving time and distance, eventually giving us a departure date of July 24th, but recommended a departure date of July 19th. Our logic here, going through from left to right, the driving hours was derived from Google Maps data, and the total days was determined to factor in the 8 hours of touring time for each city that we visited, and also for sleeping time of approximately 8 hours for every 16 to 18 hours of waking time. And then the departure date was calculated based on that, and the +1, +2, and +4 in the total days refer to the days where we had to break up the drives because they were too long, over 10 hours. As for the recommended, we include a 5-day slack time because there could be any number of issues that could go wrong when you're going on such a long trip, maybe cars breaking down, weather, or any other, or if we wanted to stay at some city for a little longer because we really like that city. So the final recommended date of departure based on the weighting that we give to each model is July 18th, because we give the highest weight to the shell method Google Maps data, and a little less to the Euclidean model, and then finally least amount to the simulated annealing model, because we know that these results are less than optimal compared to the shell method. So for our what if scenario, we're going to say that we want to visit 4 additional cities in the lower provinces of Canada. Canada is really cool, and we've all like to visit Canada as well. So these cities will be Toronto, Ontario, Montreal, Quebec, Calgary, Alberta, and Vancouver in British Columbia, bringing us to a total of 52 cities to visit. There are some practical assumptions that we're going to carry over. We are all assuming that we all hold Canadian tourist visas and driver's licenses that are valid in Canada. We're going to ignore queue and check times when crossing the border, and in personal experience, this also takes less than 10 minutes, so this is a reasonable assumption. And we're also going to assume that driving speeds are held constant in Canada and in the US for driving time calculation purposes.
While this feature is apparent throughout all our results, this solution clearly shows that the routes go through water. However, even though the map shows that we're driving on water, we're actually using the distance data generated from Google Maps, which routes the driving distances over roads on land. So only for illustrative purposes does it seem that way. At any rate, the inclusion of the lower Canadian provinces actually does not significantly increase the driving time or driving distance for the resulting tour obtained by applying the shell heuristic for Google Map data. Relative to the shell heuristic for the lower 48 states with Google Map data, the driving hours were only increased by approximately 10 hours, while the driving distances only increased by approximately 700 miles. However, these results are not particularly surprising, in that the general order and shape of the tours are largely conserved across the two scenarios.
This graph gives a solution using simulated annealing when adding 4 Canadian cities. The total driving time is 219 hours and the total driving distance is 14,012 miles, which is still a worse result comparing with shell heuristic. Comparing to the case of not including the 4 cities, the total driving time is only 1 hour longer and we only have to drive approximately 200 miles more. According to our previous analysis, we know that the driving time calculated under shell heuristic and the simulated annealing are 214 hours and 219 hours respectively. There is no travel time longer than 10 hours one time for shell heuristic, and we have 2 driving times longer than 10 hours according to the schedule obtained by simulated annealing. Add the time for sleep and the time for visiting sites, we can obtain the total days, that is 945 hours and also the 952 hours respectively. Since we would like to be back before August the 31st, we have to start our trip on July the 22nd and July the 20th respectively for these 2 solutions. Here we still suggest to apply a 5-day slack.
Our results suggest that the computationally optimal approach to tour the US would be the shell heuristic using Google Map data. We found that it was more reliable, significantly faster to compute, yields results that consistently beat all the other simulations, and overall is more easy to implement. As for incorporating the lower Canadian provinces, we actually found that incorporating them into the tour does not significantly increase our travel time, nor does it require a significantly earlier departure date. This results in more cities visited without a significant trade-off, which suggests that incorporating them into our tour, if we are interested in visiting these provinces, would be a good idea.
Considering the size variability of certain states, it may be worthwhile for us to visit more than one city for some states. For example, it would be a good choice for us to visit several cities in California, as it is the third largest by area and is the most populous state in US. Cities like Los Angeles, San Francisco are all good places for us to go.
So our final recommendation is to use the shell heuristic with Google Map data. For reference, here are all the cities in order of visit, starting from Washington, D.C., ending in Richmond, Virginia for our return back in Washington, D.C. This gives the shortest distance and time for driving, and we have to depart by 24th at the latest, but the recommended time would be the 19th to have some slack, as mentioned previously. Moving over to the appendix, so we mentioned previously that we evaluated two different methods for getting the data, the Google Maps and the coordinate-based methods. I'll just talk a bit more about each in this appendix. We use the Google Maps Distance Matrix API, which allows us to query the driving distance and driving time for up to 26 cities at a time. So we built two adjacency matrices, one for the distance and one for time, and modified them at the end to make our symmetric assumption hold. And we used Python scripts to handle the queries and parsings of the JSON output file, and then to write them out into Excel files. The second method, which we find to be less accurate, was called the Haversine formula. This is a formula that is used to calculate the point-to-point distance between geographic coordinates, and we found a publicly available MATLAB function for use here. You can find all these resources, including the script that we wrote, in these following links. So overall, Google Maps was a clear winner on several fronts in terms of the data quality. Google Maps actually accounted for the road path and speed limits when it output driving times. When we use a Haversine or coordinate method, on the other hand, we'd be getting the direct distance and assuming a fixed average driving speed. Haversine also had some inaccuracies built in due to these factors and often overestimated the distance and the drive time.
Presented here are the results obtained from applying the shell heuristic with Euclidean distance metrics instead of the Google distance data. From here, it is actually very clear that the results are relatively similar to the shell heuristic with the Google distance data. However, there are notable differences in the path, particularly in the areas such as Illinois and Tennessee. Furthermore, it was found that the overall drive time and the overall driving distance is significantly higher, in that it is approximately 10 or so hours more and about 700 miles more than the shell heuristic with the Google data.
Here is our MATLAB implementation of the shell heuristic. The capital T stands for the list of cities that are on the convex hull, and in the second for loop, we do the cheapest insertion heuristic to find the minimum distance. Next is our MATLAB implementation of simulated annealing. Here we choose the starting temperature to be 1 and the cooling factor to be 0.95. Also, the maximum iteration is 10,000. Because there are so many iterations to do, so the simulated annealing is more complex than the shell heuristic.
Thank you for listening to this presentation.